Up next, we have Emergent Complexity. This talk is by Kevin from Magnite, and Magnite are one of the sponsors today, so big thank you to them, because without them, we'd be probably doing this in a car park. But yeah, thank you, Kevin. Over to you.
All right. Thank you very much. Trying to get this full screen really quick. Sorry, it's there we go. Perfect. All right. Thank you. All right, sorry about that. So yeah, today I want to talk to everybody about an idea I'm calling emergent complexity. It's the idea that we can build complex systems with complex interactions while actually making sure every part of our code base is actually simple. Now, I'm Kevin Logan. I'm from Magnite. I'm a fellow of engineering there, and I sort of lead our engineering operations there in Belfast, which is actually our largest engineering office globally, but Magnite is a global ad tech platform. So I'm sure as developers, we've all worked on a code base where parts of it, or sometimes all of it, have become a little too confusing. And we eventually start to actually containerize this, and I don't mean Docker containerization, but we start to build boxes around the areas we know and we don't know. And more, we try to avoid the pieces that are confusing to us. And that's basically how we build up tech debt over time. We lose track of how these components interact with each other, and we basically try to avoid solutions that would involve using the more complicated parts of our software. Now, complication isn't a code problem, it's a problem. It happens in real life, it happens everywhere, it's a systems problem. One of the ultimate resolvers of problems is nature and evolution. And so we have this idea of like a murmuring of starlings. There are thousands of birds creating this beautiful, weird, complex pattern, and there's millions of patterns. They're never the same. But there's no architecture here. There's no complicated rules. There's only a few simple rules. They don't hit their neighbors. They fly towards the center, and they generally match their neighbor's speed. Those are all simple rules, easy to reason about, that produce complex, sometimes unpredictable behavior. So how can we take that idea and actually leverage it in the software we build? Build complex software from simple, understandable parts, and let's not get lost in the complexity of what it's all going to do together. So it's a little disingenuous, because our job is different from starlings. Our job is to actually architect it. There is actually an architect. There is actually someone designing the system. But that doesn't change the way we can talk about problems anyway. We can still take inspiration from this. The goal is still the same, to create a system that is powerful and complex, but where the individual components are simple, just like the starling simple rules. Our tools for finding those rules in software engineering is abstraction. It's not a tool for hiding complexity. It's a method for finding and defining simplicity. So a good abstraction is just a clean boundary around an idea or a concept. It's like a seam in our system. It gives a simple and clear name, like a steering wheel, to what might be a very complex set of interactions. As the driver here, our steering wheel component is incredibly simple. You know, turn the wheel, it turns the car. Everybody understands that. There's no complication there when we talk about it like that. At that level of abstraction, it's a simple idea. The engineer who built this system might have a completely different idea in their head. They know the how is actually complex. They might talk about things like the steering wheel, connects to the steering column, the rack and the pinion and the power steering pump all interact together to cause the wheels to turn, which causes the vehicle to turn. It's this very complicated set of interactions, but we don't actually need to talk about that unless we're designing within that system. We can just take a level higher, an abstraction level higher, and we can talk about what our individual components are. We're the steering wheel. And if you're the designer within there, then you talk about your simple components inside that. The power steering pump is not a simple component either, but you can talk about it as it interacts with the other simple components, and you can always try to frame your reference in an area where we're talking about the simple interaction of simple components. So this is exactly what a good function or API should do. It defines a clean boundary between ideas and concepts. It gives a simple name like turn steering wheel to our otherwise complex interaction, which this turn steering wheel itself is in turn using more simple abstractions like maybe calculate wheel angle and engage power steering or send angle to axle. Our naming here is creating the abstractions that keep our code simple at every step. We're building these simple ideas by composing other simple ideas. And that's our goal. Find simple composable parts. But as we all know, that's actually where things get hard. And when I think about why this is hard, it brings me back to a couple quotes. We have a quote from Phil Carlton, sorry, that, there's a joke version of it I've heard more often than the real version, but, I've heard there's only two hard problems in computer science: cache invalidation, naming things, and off by one errors. But the point here I'm trying to bring is that Phil Carlton has brought naming things as one of the principal problems in computer science. Why? Why is naming things so hard? Naming things is hard because that is fundamentally finding the abstraction that defines the interactions or the components we're trying to build. If we can't name something, we probably don't actually know what we're trying to do yet. And if we start building the code without knowing what we're trying to do, it's not going to go great. We're going to write complicated code. So then there's this sort of litmus test that I like to use. That maybe we're not talking about 6-year-olds here, but Albert Einstein has famously attributed this quote: "If you can't explain it to a 6-year-old, then you don't understand it yourself." I kind of co-opt this to mean the same thing. If you can't explain it to a 6-year-old, then you don't know the words to express the concept. Of course, a 6-year-old wouldn't understand general relativity or special relativity. They probably can't. But if you can find abstractions that work at their level and talk to it about them, you can more or less get them to understand some parts of it. But I think the quote is itself a bit tongue-in-cheek. I think Albert would have been saying that he didn't really understand it himself, which he liked to joke about. So how do we know that we've succeeded? Well, we can explain it to somebody, maybe not a 6-year-old again, but we can explain it to somebody, and that means we understand it and they can understand it. That's it, that's the goal. A good abstraction is a simple explanation. Abstraction is discovering the simple underlying ideas that can in turn easily connect into English, C++, Go, Rust, whatever, and ultimately it drives understanding. If naming then is the process of abstraction, Einstein's quote here, we can use it as our litmus test for it. So what happens when we fail this test? I have a few examples here, and we're just talking about English language here. So we don't have to talk about code yet to understand that we're already capable of solving and failing to solve abstraction problems. I have a very simple idea here in the middle here. It's like, I like to cycle to the office. I think we all know what that means, right? There's no complication. A 6-year-old gets this. It passes our litmus test. It's clear, it's concise. There's no confusion really there. What happens when we under-abstract something in speech? So, what is it? The human speaking now receives a positive dopamine response from the utilization of a 2-wheeled, pedal-powered vehicle to travel to his place of work. That doesn't sound good. We all know immediately that's wrong. Maybe it sounds like I'm trying to be technical and sound smart. Maybe it sounds like I'm drunk or something. It doesn't matter. We all know immediately that that is wrong. So we have this sort of intuition already for abstraction in language, and it doesn't have to stop there. So what if we go to like an over-abstracted version of the text here? My preferred non-motorized vehicle modality preference facilitates my daily professional commutation journey. Now I sound like I'm just talking jargon, and probably nobody knows what I'm talking about anymore. I'm trying to say the same thing, but if I don't know how to word it myself, maybe I don't understand it, and certainly I'm not helping any of you understand it. So we need to focus on finding the good level of abstraction, and we intuitively know this. We know this in English. We all know to say the one in the middle. You don't have to sit a long time and think about it to find the one in the middle. But as things do get more complicated, you might have to take a moment and think about what you're going to say. But we do still have this gut feeling that drives us towards the correct middle ground in language, that abstraction that makes sense. We can take this and we can leverage it in the way we design software. So let's look how this might work in the technical requirements or a tech spec or something of the sort in code. So say we've received requirements here. Let's start again, or this time let's start on the under-abstracted actually. We get a ticket and we basically just need to do something, right? And the ticket's gonna tell us something potentially under-abstracted like this. We need a new post endpoint at /upload. It must check the first 4 bytes for 0x dead beef. It also needs to read the entire file into memory, blah, 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 blah. It's just a stream of consciousness coming out of the product owner, tech lead, whoever wrote this. They just vomited out all of the requirements. There's no abstraction to it. There's no understanding. It's just raw data. It's under-abstracted. And it's full of magic numbers. It's got 5,242,880. It mixes what it wants, like a new endpoint, with how to build it, like reading the entire file into memory. And trying to parse and find the actual simple rules here is complicated. It's hard. It's a nightmare. This is a classic case of under-abstraction. It's just a blob of implementation details. It doesn't matter if we're talking about English, it doesn't matter if we're talking about requirements, and it doesn't matter if we're talking about code. It's the same problem happening at every stage. So if we look at the over-abstracted side, we'd call this like a jargon spec almost. It's implement the file upload orchestration saga. The saga will coordinate with the ingress validation service to apply the WTF file format policy upon successful validation, blah, 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 blah. Who knows what that's even trying to do yet? Like, we can eventually, you can imagine these are all just snippets of what the spec would actually be, but we can imagine it's going to take you a lot of reading on the under-abstracted or the over-abstracted to understand what we're actually trying to do here. But if we leverage abstraction in our technical requirements, we write something in the middle, we can start with a simple sentence, create a new secure endpoint for storing WTF files. Now, we don't know what that means yet, but we've already named all of our abstractions. Secure or security is an abstraction. Endpoint is an abstraction. WTF file is an abstraction. We have all these abstractions, and then we can hierarchically build upon them. And so we can define each of those abstractions, again, using more abstractions as we go to make sure every definition itself is simple. Your abstraction should read like a dictionary, where you can create an abstraction, you can talk about what it is, you can use other words to define it, and ultimately we need to be able to find those other words and what they mean themselves if we don't already know them. So in the middle, we have WTF files, our proprietary format. Now we know why we need deadbeef. It has a header that starts with deadbeef. We know we need a checksum, that the final 4 bytes are a CRC32 checksum. And we go on and on like this. So this is the most important part. The spec you get, or perhaps the one you write, can almost directly determine the code we're going to end up with. Because you can imagine if you start with one of these other 2 specs, one of them is kind of over-prescriptive over here, saying you're going to write this file orchestration saga or whatever, and the other one's under-prescriptive, and you're probably just going to write garbage code that looks like a garbage spec. So let's look at it. What's it going to look like? We got that wall of text requirements. Sorry, this is Rust, by the way. I use Rust, but the language doesn't matter here. It's a language agnostic idea. Hopefully it's easy enough to read all the same, but we have this wall of jargon, sorry, not jargon, the wall of requirements, just a steady spewing of requirements, translates into a steady spewing of code. Now this isn't the entire function again, as you can imagine, but it just kind of goes like this. Imagine a lot of us here are like senior engineers and we can read this and we can totally deal with this. But if your entire code base is built like this, you're gonna have a major problem on your hands. So it just does everything as it goes, body.len less or greater than the magic number we have here essentially, and we're returning a problem. Then we're checking if it's less than 9 for some reason. It might not be apparent to the code reviewers or the people who maintain this 6 months from now. When we check a magic number, and we're just grabbing a slice of the payload there in the middle, and then we're performing the checksum, and none of it makes any direct sense. You can kind of tell what it's doing, but you don't know why. How do you test this code? You can't. You have to mock a full HTTP request just to see if the checksum logic is correct. How do you maintain this? What if we want to add a second file type? You'd have to copy and paste the whole thing or add 10 more lines of code. And this thing is begging for comments, but you need a comment to explain, like the checking the magic number, for example, and another to explain checking the checksum. The code's not self-documenting. Those ideas can be expressed in code. You don't need comments for those ideas. So that's one failure, but what's the other failure? If we have the over-abstracted tech spec, we get a different kind of monster here. I don't know if you'll be able to read this one, but the point is it's over-abstracted. There's a ton of different systems, a ton of different interactions. It's not clear how they're all interacting or why. The engineer is also just following their spec here. So just like the previous example, they did what they were told, and they're following the spec, and they have this maze of types. We have an I-validation rule, validation context, IR validator objects, and a WTF validator factory to tie everything together. We built an entire validation framework just to check one file type. We have 10 new types, interfaces, and all it does is the job of 3 simple functions. So this fails the Einstein test just as badly as the previous one would have. Can you explain this to a 6-year-old? Can you explain this to an entry-level engineer? You might not even be able to explain it to a senior engineer without an hour and a whiteboard. But the idea was still simple. How do you trace this? A simple upload request now bounces between 5 different objects. It's impossible to follow the logic. And what about the comments here? The comments are just as over-engineered. They're not explaining what we're doing or why. They're explaining the framework, the needlessly complex framework we're adhering to. It's jargon explaining jargon. So this is another failure. The complexity here isn't emergent. The complexity here was introduced by us as we wrote this code, as we wrote the spec. We've created an explosion of abstractions between our simple parts. So we've seen the 2 ways we fail. What does it look like when we succeed? The code should be more or less something like this. It's obviously not the best possible implementation of these requirements, but it's better abstractions which lead to a better understanding. And this better understanding from better abstractions applies to everyone. It helps a product owner write a clearer spec. It helps the first engineer write clear, composable code. And it, just importantly, helps the next engineer 6 months from now understand what's going on here. What we see in this code is alignment. This isn't just say that you've got a good spec and you write good code. It's that good and clear abstractions lead to a good spec and good code. Now, at the left, the blueprint there, it's clean because you found the simple concepts. The WTF file, endpoint, secure. Look at the right. The code is clean because it implements those exact same concepts. Validate WTF file reads like a checklist. It's the spec translated. It's completely self-documenting. This is emergent complexity done right. Each simple rule, like has valid header, is trivial, is testable, and when we compose them, the correct complex behavior emerges. So this is the goal, right? A perfect tech spec lands on your desk, and you go write perfect aligned code. Everyone's happy, right? But let's be honest, how often does that actually happen? More often than not, we're going to end up with one of the wall of text tech specs, or the over-engineered jargon tech spec, or something that's over-prescriptive, or something somewhere in between. So what is our real job as developers? And this is sort of my central point. Our job is not just to be coders. We're not just translating tech specs into code. Our job is to be engineers and architects. If you just translate a wall of text into a wall of code, you're not engineering, you're just programming. I want you to think about the word engineer. Let's think about building a bridge. A coder, on this side? That side, sorry. A coder or a programmer is like the welder in this bridge. They're critically skilled, and they are responsible for flawlessly executing a task, connecting beam A to beam B. They are following the how, while the engineer is the architect. They are responsible for the entire system. They don't just know how to weld. They know the physics. They know why that beam needs to be there. They own the result, whether the bridge stands or falls. So you, as an engineer, own the result, whether or not your code succeeds and does what it's asked to or not. You own the result, whether or not engineers a year from now can read and maintain your code. You own the result if your code causes an alarm at 2 a.m. 6 months from now. You own that, and you got to bring that in to the design as you build the code. When we get the wall of text spec and we just translate it, we're acting like programmers. We're just welding beams as we're told. Our real job and our real value is to be engineers. It's to stop, look at the problems, and understand the physics of the system, and then own the result of it. So how do we do that? What is the process of being a software engineer and not just a programmer? This is our call to action. This is our value as engineers, to find the simple rules. Now, I know some of you might be thinking this sounds a little idealistic, or perhaps it sounds slow. We all have deadlines. It certainly feels faster to just get going and start programming. But I believe the counterintuitive truth is truth here. The engineering approach may feel slower at the start, but it is usually faster, though not always. I have to admit that. Pausing for an hour or even half a day to truly understand your problem, find the right abstractions and validate them, that's going to get you to a quicker solution much faster than spending 2 days coding the wrong thing, creating accidental complexity, and then spending another 2 days refactoring it all when you realize you misunderstood. Or worse, you don't realize it and you ship the broken thing. This is about preventing rework, and this is the first and most important defense against complexity. So how do we do this? What is the process here? First, if you get that wall of text tech spec, pause, stop. Your job isn't to be the welder, it's to be the architect. Your job isn't to code, it's to understand. Listen to your gut. There's gonna be that uneasy feeling, just like with language, but some people have learned to suppress it when you're looking at code. This code is complex, something must be wrong with me. I must not be a good engineer. I don't understand this. No, that's your gut telling you it's complex, and it shouldn't be. The abstractions aren't found yet. That's okay. Let's look about it, let's think about it, and let's fix it. Find the nouns and the verbs. What are the real concepts here? Oh, it's validation, it's storage. That's what we're doing here, okay? This is the naming problem. If you can name the concepts, you've found the abstractions. Now refactor the requirements first. I wouldn't start in the code. I'd start in the requirements. Mentally or on a whiteboard, turn the wall of text into that clean hierarchical tech spec. And then, this is crucial, go back to whoever wrote those requirements and validate your understanding. You're going to improve their understanding and yours, and you're going to find any miscommunications or misunderstandings you found along the way. But now you can code, and you'll end up writing the code that's simple, straightforward, and follows the abstractions. And it doesn't have to be a big revolutionary act here. You can start small if you need to. You can ask about one particular abstraction. Are these three things, the checksum and the deadbeef header, is that a form of validation? Can we call that WTF file validation? And you can start small, and you can work towards more and more changes to the tech spec. And that's it, you've done it. If you started the conversation, you can validate an abstraction, and you've acted like an engineer. And this is an evolution in how you work, not a revolution. So one point I would like to throw in here is how comments can help us see what's going on inside our code. They work as a sort of another kind of litmus test for our code. They're a canary in the coal mines, so to speak. You're in the code and you're trying to be an engineer. And so how do you in that moment know, as you're typing, if you found the right abstractions? A simple rule of thumb I found is look at the comments. They will tell you. Look at the wall of code here, that's on the left, it's more simplified now, but it's full of comments. You can't go and complain that this person wrote the code and didn't comment it, but what kind of comments are they? They're just narrating what the code is doing. So check if the file is too big. Okay, 5 megabytes, got it, okay. That's why we're doing body len greater than 5.2 million, okay. Check the checksum. Okay, now we know that's checksum is at the last 4 bytes of the payload. Okay, that's code smell. If your comments have to explain what your code is doing, that's probably already an issue. The code might not be well abstracted. You're forcing your comments to do the abstraction's job. Now, look at the right side, and this is just as bad. The comments here don't explain the business problem of checking a file. They explain the needless framework that was built. Run the rule against the given context. Instantiate the correct validation chain. What is that? That's just, again, jargon explaining jargon. It's totally useless to understand what we're actually doing here. Another engineer's not going to come in here and see how they can improve the code because they don't even know what you're trying to do. Now let's look in the middle. This is the quote-unquote good code. Validate WTF file has almost no comments. It's entirely self-documenting. Why would we need to? We don't need to say if not is valid size bytes. We don't need to put a comment in front of there and make sure bytes has a valid size. No, that's clearly what that reads as. We don't need to say let's comment, we're checking the file header. No, has valid header is doing exactly that. You don't need to comment that. You don't need to say what we're doing. But there is a comment in has valid checksum. What's it saying? We must use the IEE algorithm because it's the one used by the WTF protocol spec, version 1.2. What is that comment saying? It's not saying what we're doing. It's saying why. We're doing that because we have to do this. You can tell from looking at the code what we're doing, but your comment, when it's telling you why you're doing it, that's a good sign. If your comment is saying what you're doing, it's a bad sign. If your comment's just explaining your code, that's a bad sign. There are always exceptions to these rules. It is a rule of thumb. But if your code and comments frequently look like one side or the other, you haven't spent enough time finding the abstractions that let you write the code in the middle. So this is the test. A comment about what is a red flag. A comment about why is a sign of mature abstraction. So we started this talk, and I mentioned a murmuration of starlings to show how immense complexity can emerge from just a few simple rules. And I've said our job in software is to do the same. Our goal is to find those simple rules. And our tool for that is abstraction. Naming things isn't a joke. It's the hard part. It's the hard part of computer science. It's the very act of defining our abstractions. And if we cannot explain it simply, we have not found the explanation. But the most important takeaway is this. Our job is not to be coders. It's not to be welders putting beams where we're told. Our job is to be engineers, to be the architects who own the blueprint, to pause and to understand and to manage complexity before we even write it. So when you go back to your desk, be the engineer, find the simple rules, and build the systems that are not just powerful, but understandable. That's all I have. Thank you.
Thank you, Evan. Do we have any questions in the room? Or any comments? I'll bite. I suppose over-engineering, it doesn't happen all at once. It tends to happen and build up over years through various PRs and different contributors making changes. As a reviewer for a pull request or merge request, Do you have any tips and tricks for try and get it before it becomes a big problem?
Yeah, I think when you're writing the code, it can happen in baby steps, where you have a slight over abstraction or a slight under abstraction. So I think in general, build up over time tends to be more on the slight over abstraction side of things. So you might take something and be like, let's go back to the car example maybe, and say, all right, I've got a thing that has a steering wheel. I'm going to call that a car. Okay? Cool, it's a car. We have a car object now. And then 6 months down the line, they're like, well, what if it's a truck? Or what if it's a kid's toy? Like, we didn't actually say before it was a car, but we want, a little kid's toy trot or whatever, with this little steering wheel on it. We want to use all the same classes and leverage the same code, but we accidentally build up too much extraction on top of it before. And now we're saying, well, that's not really what it was meant to be. But then the product person might come back to you and be like, well, we never said that. We just said it was a thing with a steering wheel. And so when we're reviewing the code and you look at it and somebody's attributed a name to something that doesn't need to be there, that could be a sign. It's like, why'd you call that a car? I know it might be silly to call it something like thing that has steering wheel. So yeah, we're at that hard problem in computer science. What is that thing that has a steering wheel that we don't yet want to over-prescribe and call a car? And so having those conversations, talking about it, and yeah, you do have to have a vision for what's coming somewhat to understand those abstractions and where they should be, but you should make sure there are abstractions around it. And then yeah, on the other side, on the under-abstracted side, if you see somebody writing functions handling a steering wheel or something, and then a few months down the line, somebody else is writing code, interacting with that, and they're rewriting a lot of stuff, and you're like, well, this is very similar to what we did 6 months ago. Now is the time to pause and say, okay, there's an abstraction around these two concepts we should define. And it will create a better solution, and most of the time it will be just as faster to implement it. So we find those, we pause and we think about it as we see them come.
Thank you. Any more questions? 7-second rule. Okay, that's us. Thank you, Kevin.
Thank you very much, everybody.